At the beginning, people would turn on their cameras, but now, 2 years later, it's just like, yeah.
Yeah, she opened up the yes, it. Today's seminar the room for 30 the same the other
Zoom meetings, you got. I actually did that. Yes, thank you so much. I never talked to you. Yeah.
So if you can do it for
Yeah, I know that, especially, I mean, it's been quite a long time. Like, and there's not enough, like, transition for everybody that you do. Everybody. What is? What?
I don't think it's right away.
Did you just set up? There was something we called.
Yeah. I bought my car here, so. That makes sense. Yeah. I know, we're having a talk. It may be, I mean, the whole. Sorry. Just get one. Yeah, no, I got these. I'll just make you up. And then I can do whatever I want. That's fun. Yeah, you know, didn't want to do that. I was reading it, but you know, and I pulled it out. But I can advise like something to it, but I would just not. Sometimes they don't want to start looking 11 to 2 or get people and then they're trying to get in. Yeah. I felt like he managed.
Requesting the code doc. I just. You can. No, you don't need to do nothing.
Okay.
Even we can check the chat and let you know what questions.
Okay. Yeah. I'm just gonna give people another minute or two. Oh, what? Is it the clicker?
No, that's not particular. That's actually the camera. The green that we put in
That's fine, yeah, yeah. Just like we were talking about. It's a new thing, yeah.
Planning around the word next plan. Something.
Yeah, it's fine. Yeah.
Next plan?
That's what I was before I came to you.
Oh, beautiful.
It's a big, nice place.
Yeah.
Yeah.
But the
Maybe
weather
just
is
meant
good.
Germany to
Uh,
Australia
yes.
and Germany to Texas.
Completely different.
Yes. Especially like public transportation in Germany. Impeccable, you know, and then moving to Austin, but don't tell me.
Hey, Austin's the best to get
That's
infected.
what you told me, and like stop, you know,
Yeah.
So how long you stay in Queensland for 1 day?
just 7 months. So I just deferred my UC offers for the last year.
Much better. We'll still look for a person for.
Okay, lots of people coming in.
Yeah.
We'll give it another minute or two so people can get pizza.
Oh, yeah. Yeah, yeah, yeah.
And many people from the main campus, organized by bar, or maybe by.
Yeah. Really. That's a great question. I don't know the answer.
I remember around 10,000 per.
Okay.
Right.
See?
I know, well, I just have to,
Yeah.
but I think it's like,
Faculty who are based on.
I would have to get that. But it's, yeah, like to me, it's like a big state school, so I would want to say like, oh, well, like you have Madison has about 30,000 residents, but I think UT does too in my mind, but I think Texas, with the scale of everything is so much bigger, and then also there's so many more universities too, so it's
True.
How many classes do you have?
All right. It's my pleasure to introduce our speaker for this week, Dr. Jullia Lindberg. Dr. Lindberg is a postdoctoral researcher in UT Austin's math department. And before that, she was a researcher at the Max Planck Institute in Germany. She got her PhD in electrical engineering, electrical and computer engineering. So welcome, Julia.
Thank you. Yeah, thanks everyone. Yeah, thanks for the invitation. So I'm actually going to talk about a little bit of older work, so some stuff from my PhD thesis, but I was hoping that maybe it'd be of interest to maybe more of the data science. And I should note that this is joint work with Carlos Amendola and Jose Rodriguez, who is one of my PhD. So to begin, so kind of very common and classical problem in statistics is what's known as density estimation. So what this says is, suppose I give you n samples and they come from some unknown distribution P, can we estimate what P is? Now, in order to have kind of any hope of solving this problem, we usually need to make some assumptions on the distribution P, i.e. we need to assume it lies in some family or it takes some shape, something like this. And this is the type of information that maybe a priori we wouldn't have, right? If I just gave you a bunch of data, it's not clear, say, what family of densities this data belongs to. But the following theorem gives us a nice family to select. And what this theorem tells us is that Gaussian mixture models are universal approximators of densities, in the sense that any smooth density can be approximated arbitrarily well with a Gaussian mixture model. So kind of what this means for us in practice is maybe my actual density isn't a Gaussian mixture model, but if I assume it is one and it has enough components, then kind of for all intents and purposes, it'll be good enough because it'll approximate the true density arbitrarily well. So this really motivates our study of density estimation for Gaussian mixture models. So I'm sure I don't need to say this, but just to really make sure we're all on the same page, a Gaussian random variable is a random variable with this exponential density. Then a Gaussian mixture model is just a convex combination of k Gaussian densities. So on the left here, we have our standard normal 0, 1 density, right? So it's unimodal, symmetric, very nice. And then on the right, we have a mixture of 2 Gaussian densities. And so off the bat, you can already see how much more expressive these mixture models can be, right? So this is bimodal, it's not symmetric. And so maybe you can kind of start to believe that, okay, if I had enough Gaussian components, I could sort of approximate, you know, that's very expressive. Okay, so let's state our problem. So I'm gonna give, or you're gonna give me n samples, y1 to yn, and you're gonna tell me it's distributed as a mixture of k Gaussian. So this kind of in and of itself is a little bit of a problem that I'm brushing under the rug, right? How do I know what k to select? Not gonna be the problem of consideration. So I'm just gonna assume you tell me it's distributed as a mixture of k Gaussian. How can I recover a mean, a variance, and a mixing coefficient for each Gaussian component? Well, you know, if you've kind of taken a stats class, there's probably one idea that would immediately come to mind, and that would be to do maximum likelihood estimation. So maximum likelihood estimation is this very popular, well-studied optimization problem in statistics that's really well named. So I'm literally trying to maximize the likelihood that my samples came from a given distribution. Now, in the case of Gaussian mixture models, this problem looks something like this. Now, it's a little bit of a mess to kind of look at, but maybe you can believe me that unless k equals 1, this is going to be non-convex, right? So kind of off the bat, I'm only hoping for any sort of local information. There does exist an algorithm that can find these local optima, namely this expectation maximization, or EM algorithm. But the guarantees are pretty awful on this. So it's been shown that these local optima can be arbitrarily bad with respect to this objective function. And moreover, random initialization will converge to these bad points with high probability. In addition, it's also been shown there's no sample size independent bound on the number of critical points, meaning that, you know, in some applications, right, we have, say, finitely many critical points. Maybe I could try to enumerate all of them and then select the best one. That's not really practical in this situation. In addition, in order to run this EM algorithm, you need to access all samples at each iteration, and so this can be prohibitive for large systems. So kind of long story short, maximum likelihood estimation is a kind of very powerful technique, computational technique in statistics, and for some families of distributions, it works very well, but these Gaussian mixture models are just not one of those things. So okay, we need another idea. And the second idea is also another kind of very classical method known as the method of moments. So the method of moments estimator is consistent in this case. And so what that means is as my number of samples tends to infinity, this method, if I kind of use this method of moments estimator, I'm guaranteed my estimator will converge to the true underlying distribution. In addition, and this is something I'll talk about in much more detail later, but Gaussian mixture models are identifiable from their moments and specifically from finitely many moments. What this tells us is that this is a finite dimensional problem. And so here's kind of the big if. If I can solve these moment equations, so if I can actually kind of run the method of moments to compute this estimator, then at least in the population setting, I'll be able to recover the exact parameters of my underlying distribution. And so all of this really motivates our study of trying to kind of make the method of moments computationally realistic for these Gaussian mixture models. Okay, so let's lay out this method of moments. So if I give you a random variable x, its ith moment is the expected value of that random variable raised to the ith power. A key feature of moments is that for parameterized distributions, moments are actually functions of the parameters. So what do I mean? For a Gaussian random variable, a Gaussian random variable is parameterized by its mean mu and its variance sigma squared. Then I can actually compute the first couple moments, and you see this first moment is just mu, the mean, as we know. The second moment is mu squared plus sigma squared, third moment, and so on. And so you see, like, each of these moments are actually functions of these unknown parameters. So the way the method of moments works is I consider some statistical model with, say, p unknown parameters, and then I consider the moments up to order big M as functions of this parameter theta. So step 1, I take my data, I compute my sample moment. Then step 2, I solve this system of equations. I set my sample moments equal to my moment equations to recover the true parameter. So in the case of these Gaussian mixture models, you know, the step 1 is to figure out what these moment equations are. But, you know, like many things Gaussian, moment equations of Gaussians can be kind of quite easy to compute. And specifically, they can be calculated recursively as follows. Then moments of mixtures are just mixtures of the moments, kind of by linearity of expectation. The moments of the mixtures of K Gaussians are just the convex combination of the moments from each individual component. So these equations are really easy to compute. And now I know this, looking at them, it's probably not clear what they are, but we can just maybe start to build ourselves up a little bit, right? So let's take the easiest case when I just have a single Gaussian. So this isn't a mixture model, but we can still kind of go through this. Well, in this case, if I look at the first 3 moment equations, I get the following system of equations. So just remember these M1 overline and M2 overline, these are numbers, right? These are numbers I compute from my sample, from the sample. Well, I can actually just solve this closed form using essentially basic high school algebra, right? The first equation gives me lambda1 equals 1. Then I can substitute that into the second equation to get that mu1 is equal to the first sample moment, and then so on. So in this case, there's a unique solution given by the method of moments, and it's kind of very easy to compute. Okay, so let's look at then what happens when k equals 2. Okay, well, you know, you can already see things start to kind of accelerate quickly, right? So when k equals 2, here are the first 6 moment equations. And one observation to see is that we have some symmetry here, right? So if lambda1 mu1 sigma 1 squared is a solution, lambda1 mu1 sigma 1 squared, lambda2 mu2 sigma 2 squared, if this is a solution to this system of equations, then so is what happens if I just permute the inputs, right? And so this symmetry is called label swapping. It's kind of incredibly well documented in the statistics literature, and specifically with respect to these mixture models, because this type of symmetry will always exist. But I just really pointed out so that we know when we say kind of recover the parameters, I only mean up to this label swapping symmetry, but you know, for all intents and purposes, this is okay, yep, so for the K mixture model, solutions will come in groups of K factorial. So in other words, we have this symmetric group on K letters acting on a group. Okay, but this K equals 2 case actually kind of, as you can see, it's already not trivial, right? And the study of Gaussian 2 mixture models started with Carl Pearson over 100 years ago when he was studying measurements of Naples crab population. And so what happened is he was collecting these crabs, measuring the length and the width and the ratio, and then recording the ratio. And he got the following data set here. And so what he saw and what you can see is this data is a bit skewed and maybe multimodal. And so he actually conjectured that, well, he's not observing the measurements from a single Naples crab population. What he's actually observing are probably 2 separate subpopulations. And so he proposed using the method of moments to recover the parameters from each of the 2 subpopulations. And so he solved this polynomial system that you see here. He reduced solving the system to finding the roots of a degree 9 polynomial in this variable x, which is equal to mu1 times mu2. So just note that he essentially broke this label swapping symmetry. And so he, and then reduced this to finding the roots of the degree 9 polynomial. For those of you who are a little bit algebraically inclined, he computed an eliminant, essentially, but predating any sort of Grosvenor basis theory or computer algebra software. And so what we want to do, oh, and sorry, let me just mention one more thing. So he ran through this method of moments, reduced solving the system to finding the roots of a degree 9 polynomial, solved these, back substituted to find all of the other solutions. And what he found is that in this case, there were actually, you know, up to this label swapping symmetry, 2 statistically meaningful solutions. And when he plotted out the 2 solutions against his data, both of them were actually pretty reasonable estimates for the density. So then the one he actually ended up going with was the distribution that most agreed with the 6th or the next sample moment. And so his procedure essentially was to solve this square system of polynomial equations, select the statistically meaningful solution, then that is closest to the next sample moment. And so this is essentially the algorithm that we want to repeat, but for more than just k. So formally to lay this out, the way this method of moments works here is for I equals 1 to 3k minus 1, we are going to compute the sample moment. Then we'll solve this square system of moment equations over the complex numbers to get finitely many complex solutions. So the reason we're doing this is something that will become clear in a minute, but kind of largely speaking, it's just because the complex numbers are algebraically closed, and the number of solutions to this system of equations will be generically constant. So we actually have methods to do this solve. Okay. And then after he solved over the complex numbers, he filtered out the statistically meaningful solutions. So these are real solutions that correspond to actual Gaussian, or that could correspond to actual Gaussian density. So real solutions with non-negative mixing coefficients and positive values. And then from there, he selected the statistically meaningful solution that agreed, or most closely agreed with the next sample. Okay, so this is the procedure we want to follow. I think it's pretty straightforward, but there's a lot kind of that I'm brushing under the rug that maybe should give some of you some thoughts. So step one, that's actually not so bad. Step two, this solve. As I said, we'll talk about this in a bit. Let's not worry about that right now. But solve to get finitely many complex solutions. Well, you know, how do I know there's finitely many, right? Just because I have a square system of equations, that doesn't mean I have finitely many solutions. Even in the linear case, right? That doesn't need to happen. So, okay, that's kind of a big assumption. And then this next one, select statistically meaningful solution agreeing with next sample moment. Well, how many moments, right? And how do I know at some point that there will be a unique solution that agrees with the next sample moment, right? And so what both of these issues are really issues of identifiability. And so this is kind of the first step before we kind of just throw ourselves into this method of moment stuff, is we really need to understand the identifiability of our distribution from its moment. And I claim that there are different notions of identifiability, but I can define them all based on the fiber of the following map. So I'm going to consider this piece of big M. And what I'm going to do is I'm going to map my simplex, so my actual kind of mixing coefficients, as well as means and variances. So kind of the set of all possible Gaussian K-mixture models. And I'm going to map them through the moment map. Then what I'm going to do is I'm going to take a point in the image and I'm going to say, okay, how many Gaussians corresponded to that point in the image? So the first thing I mentioned was I saw the square system of polynomial equations, I get finitely many solutions. So what that is saying is that for if I take a point in the image, that I want the pre-image or the fiber above this point to be finite. And I'm going to add this assumption for almost all points in the image. And what I mean is for some Zariski open set in the image, or in other words, what I mean is off a set of measures 0 in the image, I want this fiber to be finite. This is a really mild assumption because, you know, in practice, I'd have samples. And so my moments would never exactly lie. My sample moments would never exactly lie on a set of measures 0. So it's really mild, but it, you know, makes it's kind of, once we work go into the world of algebraic geometry, being able to say lie on Zariski open sets makes our life a lot easier. And so this question has actually been answered. And it was shown that if you take 3k minus 1 moment, that this fiber will be finite for almost all points in the image. So this first statement I said about solve this square system of polynomial equations to get finitely many solutions, this is actually a legitimate and okay statement. But if you ask a statistician, you know, about identifiability, this isn't what they will have. So what they have in mind is what, you know, what they would just call identifiability, what I would call statistical identifiability. And what they want to know is, okay, so what M, and this is this big M, this is my number of moments. So how many moments do I need such that the fiber above a point in the image is K factorial, but really this is just 1 up to a label swapping symmetry for every single point in the image. So they're dropping this almost all assumption, and they want a unique point in the image. And this question was actually also answered. And it was shown that you need 4k minus 2 moments to uniquely identify every single Gaussian mixture model. In addition, this bound is tight. So there exist 2 Gaussian mixture models that have the same first 4k minus 1 moment, and you can only uniquely identify them once you look at the 4k minus second moments. But such Gaussian mixture models are really special. Namely, for instance, if all of the means are 0, then the every odd moment equation just becomes 0 equals 0. And so you get no new information from it. So then you really do need to go up, this high to kind of uniquely identify. And so what I'm trying to say is that this for all is actually kind of really restrictive. And you see there's an order of magnitude gap here, right? So to get finitely many, we needed 3k minus 1, but to get unique, this result is telling us we need to look at an additional k moment equation, which just feels like way too much. And so for that, I'm going to introduce another notion of identifiability, which we call rational identifiability. And this is essentially in between algebraic and statistics. So what I want to know is how many moments do I need such that the fiber above a point in the image is k factorial, or is unique up to this label swapping symmetry for almost every point in the image. And so this is kind of one of the first new results we have. And we show that these mixtures of k univariate Gaussians are rationally identifiable using just the first 3k plus 2 moments. So again, because in practice we'd be dealing with samples, this almost all assumption is met with probability 1. It really is. And so what this result tells us is we only need, on the order of 3k moments to really uniquely identify all of the mixture. I'll just say, we conjecture that you really only need the first 3k, which makes sense, right? At 3k minus 1, I have finitely many, so I think I need just one more to get down to a unique one, but we couldn't prove it. We needed the extra 2. And the way we were able to prove this is using some recent results on the secant of variety, so kind of a nice classical topic in algebraic geometry. Okay, so we've kind of covered a lot here, and let's go back to our framework. So we're going to compute our sample moments. We're going to solve our moment equation to get finitely many complex solutions. We just justified that actually is the case. In addition, we're going to then filter out statistically meaningful solutions. That's easy. And then now I can say that I'm going to select the statistically meaningful solution, agreeing with the next 3 sample moments. And from the results I just mentioned, this is all justified. So kind of the only thing missing here, and it's a big missing one, is this solve is kind of doing a lot of work, right? So how do I actually solve a square system of polynomial equations? And for this, we're going to take a little bit of a detour into some numerical algebraic geometry. So I'm going to just give you a really high overview of some general methods for solving square systems of polynomial equations. The big takeaway is that there exist methods, and if that's all you get, that's okay. Then we'll come back to our problem in a minute. Okay, so I'm going to consider a system of n equations in n unknowns, and I denote its complex variety by v of x. So this is just a set of common zeros of n polynomial equations. We are interested in the square case, i.e. where the number of variables equals the number of equations, and moreover, we're under this assumption where our variety is finite. So another way to say this is that I've got a complete intersection. So I've got some variety, and it's got, in other words, I'm just ignoring all other structure. I've got finitely many points. I've got a set that has finitely many points. The first question you'd ask, right, is, well, how many? And there's this 2 pretty classical results that tell us this. So the first is by Bezout. So this is probably the most classical. And what Bezout's bound tells us is that the number of points in my variety is bounded above by the degree of the product of the degrees of the polynomials. So this is kind of really easy to compute, right? I just multiply n numbers together and I'm good to go. Moreover, this bound is generically tight. So if I take kind of full monomial supports polynomials and I put just generic coefficients on them, or think of them as putting random coefficients on them, then this bound will be achieved with equality. But the issue is that the polynomial system we're looking at, and in applications in general, is not generic in that sense. Specifically, they're sparse. So kind of a priori, we know some of the coefficients will have, some of the monomials will have a coefficient of 0 and so on. Then in this case, this bound can be a strict upper bound, and moreover, it can actually just be arbitrarily bad. So for that, we need another result. And I'm really gonna just state it without saying much about it, but it's this thing known as this BKK. And the first thing to note is that I'm intersecting my complex variety with the torus. In our case, this is, I mean, for the theory of this theorem, it's really important, but for our case, it's not, this doesn't matter at all because all of our solutions will lie in the torus. So this is fine. But okay, so what it tells us is that I can upward bound the number of the points in this variety by something known as the mixed volume of the Newton polytopes of the polynomial. Again, I'm really not defining any of this, so I don't expect you to know what it means, but at a high level, for each polynomial, I can associate a polytope to it. I can take the convex hull of its monomial support. And then once I have a collection of n polytopes, I can define a function on it known as the mixed volume. And this mixed volume will output a non-negative integer. And what this theorem tells us is this non-negative integer upward bounds the number of solutions. Moreover, you can really easily get the Zoo bound as a corollary of this BKK bound. But there's a catch, and that in general, it's actually not easy to compute the mixed volume. In general, it's short p. But okay, there's a theorem, at least, so that gives us something. And I should mention again that, this bound is generically tight, meaning that for my non-zero monomial, if I kind of randomly assign them a coefficient, this bound will be achieved. Okay, so this kind of gives us the first step. I've got some set, and I've given you two ways to bound the number of points in the set. That's actually not really what we want, right? We want to find the points in the set. And to do this, there's this there's multiple methods, let me say, but I'll highlight a really broad class of algorithms known as homotopy continuation algorithms. And the idea behind this is that solving most polynomial systems is hard, but some are really easy. So for instance, the system on the left here, this is an instance of these Kuromoto equations, if anyone's a physicist. And it's a system of 4 equations and 4 unknowns. And I don't know any solutions to this. Maybe if you gave me some paper and a pencil, maybe we could do some algebra, the high school algebra, and try to work out a couple. But in general, it's not so easy. On the other hand, this system on the right here is also a system of 4 equations and 4 unknowns. And I know all of the solutions to them. I don't even need a computer or pen and paper, right? There's 16 solutions where each coordinate has plus or minus 1. So the idea behind homotopy continuation is, can I map my solutions from my easy system, the one where I know all the solutions, to my target system, the hard system, the one I actually care about? And for example, sure, you can do what you want, but one way to do this is to define what's called a homotopy. And so here's an example of a straight line homotopy. So in other words, I'm taking a convex combination of my 2 systems. And what I do is I start when t equals 0. And so I'm at my start system here, and I have all of my solutions. And I just numerically track them as I vary t from 0 to 1. Doing this is called following homotopy path. And this is typically done using some standard methods in numerical analysis. These so-called predictor-corrector methods, where you predict, you take a step in a tangent direction at a point, and you correct using something like these methods. I'm brushing a lot under the rug here, and I'm really not going to talk about more, but for those of you who do anything numerical, it's like anytime you use a numerical algorithm, everything can go wrong, and of course that can be the case here as well, but I'll just say, like, by and large, these algorithms are quite reliable, and there's a lot of theory that's been developed that kind of handles all of the situations. So in a picture, this is how I kind of think of homotopy continuation. So this left picture, this is my kind of big global picture idea. I'm going to start when t equals 1 with my easy solution. And then as t varies, I'm going to just track them along this curve defined by t until I get to t equals 1. These are the solutions I care about. Now, if I zoom in on the red curve, the way I actually kind of track this is that I discretize the curve, and I do this predictor-corrector stuff. So I kind of predict, I take a step at a tangent direction, then I correct to some epsilon tolerance using these. So we've kind of almost given ourselves everything we need, except there's kind of one main outstanding question, and that's, how do I pick this easy start system, right? The only thing I told you is you need to pick a system with a number of solutions, where the solutions are easy to find. This should be clear because otherwise I've got a bit of a circular problem. The other thing is you want to pick a system that has the same number of equations and variables, so that when you define your homotopy, the numerical stuff to track actually, like, your dimensions line up. But okay, that's not very many restrictions. The main thing here is that we want to pick a study system such that the number of solutions are kind of roughly equal to the number of solutions of our target system. If there's fewer solutions to our study system than there are to our target system, we have no hope of finding all solutions in our target system. But if the number of solutions to our study system is much, much bigger than those to our target system, then we're doing a lot of wasted computation because essentially these paths will diverge. So this really brings us back to the first thing we talked about, and why knowing the number of solutions in your variety is important, is because it helps us pick a study system. So if your variety roughly achieves the Brazil bound, then something known as a total degree study system is suitable. As you can see here, this is an example of the study system I gave at the beginning. And you can see the study system achieves the Brazil bound. In addition, it's really easy to compute all the solutions so that, it's all just, roots of quite nice. But if the Brazil bound is like a much larger upper bound than your actual number of solutions, and the BKK bound is much less than the Brazil bound, something known as a polyhedral study system is suitable. And this I can't really write down in closed form in general, but it's just a collection of binomial systems which we can solve binomial systems efficiently using linear algebra. The catch, though, and as you might have guessed when I said computing the mixed volume is sharply hard, is that, well, in general, finding the study system can be a computational bottleneck. It can be quite hard to do this. That being said, there does exist an algorithm that finds this binomial study system, but it experiences this bottleneck. So kind of once your system gets too big and that's not really well defined, it'll just fail. So just to see a quick example, suppose I wanted to solve this system of polynomial equations. So here it's a system of 2 equations and 2 unknowns, and they're both quadratic. So here my total degree study system would look something as follows. And this has 4 solutions. Then my polyhedral study system, which I could just compute by hand in this case, is the following binomial system. And you can see that this actually only has 2 solutions. And so in this case, the BKK bound is kind of strictly less than the Bezout bound. And so if we use this polyhedral study system, we'd save ourselves some computational energy. Okay, so that is all for the kind of algebraic geometry in 10 minutes part. If that went like completely over your head, that's okay. It was a lot. The main takeaway again is that there's this tool, so when I say solve, there really does exist ways to solve it. And there's this off-the-shelf software that does it quite reliably. Okay. Back to our problem. So, our framework, if we remember, we're going to compute sample moments, solve the moment equations that we now know how to solve them. To get finitely many complex solutions, we showed that this will happen. We're going to filter out the statistically meaningful solutions. That is easy to do. And then I'm going to select the statistically meaningful solution, agreeing with the next 3 sample moments. And again, we justified why that. Okay, so the thing is when you start to go through the statistics literature on these Gaussian mixture models, what you see starts to happen is that people cite this universal approximator theorem, and then they immediately restrict to subclasses of Gaussian mixture models and don't justify any sort of universal approximation of these subclasses. And so in line with that, we're also going to do that. We're going to kind of claim that these Gaussian mixture models are universal approximators and it's such a broad class to study. And then we're going to immediately restrict ourselves once we get past identifiability to some of these special cases. Okay. And so there's 3 special cases that are really commonly studied. The first is where the mixing coefficients are assumed known. So in other words, this is like I know the weight of kind of each subpopulation in the mixture. Second is where the mixing coefficients are known and the variances are equal. I'll just note that typically they will additionally assume that the variances are equal to 1, right? So not just equal, but equal 1. And then the final case is that where only the means are unknown. So you see in each separate in each separate case, I'm assuming that I know more and more about my underlying mixture model. And what we're able to show in these cases is that in all of these cases, Gaussian mixture models are algebraically identifiable using moment equations of lowest degree. Moreover, we're able to give a mixed volume to each set of equations. So let's just kind of post what this means for the first case. So I'm assuming that my mixing coefficients are known. In other words, the weights, the lambda i's, these are known parameters. So in this case, I've got 2k unknowns, namely a mean and a variance for each component. So I know that I'll need at least the first 2k moment equations to get down to finitely many solutions. And what we show is that, yep, in general, that will be exactly enough. Then once I'm at finitely many solutions, you can ask how many are there, and we're able to compute this mixed volume upper bound as 2k minus 1 double factorial k factorial. So this, problem that in general is showed how we're able to give an easy closed form. We conjecture that this bound is tight, but we can only kind of computationally verify from small things. We then give other similar analogous results for the other 2 cases, but just in the final case where only the means are unknown, we can show that the mixed volume. Okay, so as we're kind of talking about like solving the polynomial systems and finding the number of solutions, this mixed volume in general is quite difficult to compute. And so if you're going to put effort into compute it, you'd hope that it's significantly better than the Bezout bound. Because otherwise, it's like, what's the point? With the Bezout bound, I just need to multiply n integers together. So in this first case, we see that this mixed volume is significantly better than the Bezout bound. Namely, this ratio of mixed volume over Bezout bound goes to 0 as k goes to infinity. So for kind of large enough k, our bound is arbitrarily better. In the second case, this mixed volume bound is half as much as the Bezout bound, so you're kind of always beating it by a factor of 2. In the final case, they're the same, but I mean, you can't win them all, right? So what this table suggests, though, is that at least in these first 2 cases, if I was actually going to run the method of moments on these cases, what I'd want to do is I'd want to use this like polyhedral style homotopy. But as I mentioned, there can be this bottleneck in computing this system. So one nice thing about our results here is that our proofs of the mixed volume in the first 2 cases are constructive. In other words, we run through the polyhedral homotopy algorithm to get to it. And so it actually gives a system that tracks mixed volume number of paths. So it's not just a number, but really, in some sense, you can think of it as an algorithm to take you to find out the stage. This final case doesn't seem so interesting, and it's maybe not, but kind of a lot of, especially recent results, they assume when these Gaussian mixture models that the weights are uniform, so just 1 over k, and that moreover, the sigma I squared are equal, and again, they usually actually assume it's just 1. And so in this case, they're just estimating the mean. And from our moment equations and this kind of these bounds here, you can see that, well, actually, in this case, there's just a unique solution up to symmetry, up to this label swapping symmetry. So if you use the methods of homotopy continuation in this case, it's going to be really easy, because all you have to do is track one path, and you get your solution. Another way to say this is if you run Newton's method on this, right, and it converges, then you know you have found all solutions. And so this final case is actually kind of quite computationally easy if you look at it through the lens of some of this polyhedral geometry. Okay, and so in maybe like the last 10 minutes, I just want to briefly highlight how we could take this to higher dimensional models. So essentially, I want to play the same game, but I don't want to consider univariate Gaussian mixture models. I want to consider multivariate Gaussian mixture models. Here's just an example of a Gaussian density of 2 dimensions. So same game. I'm going to take my moment equations, write them out. It's a little bit more complicated to get them, but it's still pretty easy. I'm going to write out my moment equations and then try to solve my system of equations, select the next one, and so on. But maybe off the bat, you can already see this is not so easy. So in kind of the simplest non-trivial case, I've got a mixture of two Gaussians in two-dimensional space. And here I have 12 unknown parameters that I'd like to estimate. Now I can list the moment equations up to order 3, and I've got 10 of them. What this means is I need to go into my moment equations up to order 4, but there's 5 of those. And so, in other words, because there's no longer a unique moment equation of lowest degree, it's just not even clear how to set up this, like which moment equations you want to look at. So we kind of, just the initial setup of the problem, I guess, it becomes a little bit less clear. But, you know, there's a really nice fact about Gaussians, and maybe if you've been looking at this long enough, you'll see is that some of these equations look quite familiar, right? These look a lot like the univariate, the moment equations for univariate Gaussian mixtures, but just with an added index to kind of represent the dimension. And so this is the key moment, right? That the kind of all 0 except for the t coordinate, this itth order moment is the same as the itth order moment for the univariate Gaussian mixture model. And what this tells us is that density estimation for high-dimensional Gaussian mixtures just becomes multiple instances of one-dimensional problem. And again, this just really stems from the fact that the conditional of a Gaussian is still Gaussian. And so because of this nice property, we can kind of reduce our high-dimensional problem. A key advantage here now is that as we run through kind of the framework we talked about earlier, we only need to keep a best statistically meaningful solution. So in other words, once we break it down by dimension, we don't get this combinatorial mess of trying to patch together all of our solutions. So kind of high level, how this works is I put a set of sample moments in, and then I output parameters that correspond to these sample moments. So step 1 is I'll solve this general univariate case, so long as k is less than or equal to 4. I kind of didn't talk about that, but we can solve this with k less than or equal to 4 to get mixing coefficient as well as our mean and variance for one of the dimensions. From there, I will look at the next 3 moments, and I will select the statistically meaningful solution that most agrees with these next 3 moments. But now that I know my mixing coefficient, it all reduces to the case we talked about earlier, the known mixing coefficient, right? So I can use these to then solve the remaining cases n-1 times for the remaining n-1 dimensions to obtain the remaining means and variances. Again, I'll select my best statistically meaningful solution. So at this point, I know my mixing coefficient, all of my means, and the diagonal entries of my variance matrices. So all that's left is to get the off-diagonal entries of the covariance matrices. And there exists lower order mixed moments that are linear in the other entries. So once we know everything, then solving these off-diagonal entries just becomes a linear solve. Okay, so what this would look like in an example, we'll go back to our case k equals n equals 2. And suppose I input these sets of sample moments. So this first set is for the general case. The next set is to get the remaining means and variances. And then the final set is to get the off-diagonal entry of the covariance. Okay, step 1, I'm going to solve this general case. We could use Pearson's method, or we could use kind of more advanced numerical methods. And up to symmetry, you'll see that there's 2 statistically meaningful solutions. So then when I look at the next sample moment, the next moment that will correspond to each of these 2 distributions, I see that this first distribution has moments that exactly agrees with my inputted sample moment. So in this case, I would select this first solution. Now that I know my mixing coefficient, I will solve this smaller, simpler system to get the remaining mean and diagonal entry of the variance. Here, there's only one statistically meaningful solution, so okay, step 4 is quite simple. Then at this point, I just need to recover the 2 off-diagonal entries of my covariance matrices, and I use the remaining 2 sample moments to do this. There's a unique solution, of course, it's a full-rank linear system. And then all I have to do is kind of puzzle piece all of my solutions together, and I can estimate that our samples came from this density. And in this case, they did, because I didn't use sample moments, I used exact moments. And that is a feature of the identifiability, right? That if I use exact moment, I will exactly recover my true underlying density. And so just a couple of remarks. Steps 3 and 4 can be run in parallel. So once I know my mixing coefficients, I treat each dimension independently until I go to get my off-diagonal entries of my covariance matrix. So these could all be run in parallel. In general, I need to track this many homotopy paths, which is a mess in K. But the kind of key feature here is that the number of homotopy paths is linear in N. And so a lot of times in numerical algebraic geometry, we kind of consider the complexity of our algorithm by the number of homotopy paths we have to track. That's not quite the best way to do it because homotopy paths aren't really of unit cost computationally in the traditional sense, but so long as everything's well enough behaved, it kind of is. At the very least, this gives us an upper bound on our complexity, sorry, a lower bound on our complexity, and the lower bound tells us that we can expect a linear inspection. I'll just say it's even simpler in cases where some of the parameters are known, some of the special cases I mentioned earlier. It becomes maybe one numerical algebraic geometry solve and then a couple linear algebra solves. So things kind of really simplify. Another note is this whole time I've been talking about density estimation, but what we've actually been doing is parameter recovery, right? So density estimation says, I want you to give me a Gaussian mixture model that is close to the true Gaussian mixture model. Parameter recovery says, I want you to give me parameters of a Gaussian mixture model that are close to the true parameters of my Gaussian mixture model. Of course, parameter recovery implies density estimation, right? So you can just plug it into the density. But the reverse is absolutely not true. So here is an example of two Gaussian mixture densities with 3 components, and they have the same first 8 moments. For the purpose of density estimation, either of these would be fine. And there's actually 2 here. Maybe you can just kind of a little bit see up here that they're like blue peaks out a little bit below. But I mean, really, they're very much the same density function, right? Now, if I break apart the actual components and look at the actual parameters that give you each of these functions, you can see they're quite different, right? So for instance, here we have one subgroup has weight 60% versus the highest one over here has weight 45%, and so on. And so you can just kind of see that if you actually care about understanding the parameters of your subgroups, for the case of Gaussian mixture models, density estimation isn't going to give you enough. In maximum likelihood estimation only does density estimation. The method of moments actually does correct. Okay, and then in addition, just some computational results, because yeah, anytime you have a numerical algorithm, the chance for numerical things to go completely haywire is not 0. And so I just want to kind of really demonstrate that these homotopy algorithms in this case perform reliably as we think they should. So here I did this method of moments on the mixture of 2 Gaussians, and I varied the dimension. And so what you can see here is in the first row, the time really does scale linearly in the dimension. And so this was just on my laptop. I didn't parallelize anything. But for instance, I can kind of do this density estimation for a mixture of 2 Gaussians in 10,000 dimensional space in a little over a minute on my laptop. These next 2 rows, these just give you the error induced by doing the homotopy continuation. So I used exact moments, but still this homotopy continuation is a numerical algorithm, right? But what you see here is that this is essentially negligible. It's like we're pretty much at machine precision. So these algorithms perform incredibly reliably in this setup. Okay, and then I'm pretty much at time. So just to kind of wrap up, big takeaways from this talk is we're able to give new rational identifiability results for the general case of Gaussian mixture models, as well as new algebraic identifiability results for special classes of Gaussian mixture models. In addition, we gave upper bounds for the number of solutions to these mixture models, and then used those results to kind of come up with algorithms to do density estimation for Gaussian mixture models and high dimensional space. And the paper is on the archive, and so yeah, happy to take any questions.
let us look at, so much. I have a question. Yeah.
Mhm.
So you said that you implemented these algorithms on your laptop and find out what's the error and the time runtime, right?
Mhm.
Are there any legacy programming languages such as MATLAB or C or C++, where they use inbuilt, like they have their inbuilt algorithm using homotopy?
Yeah, so I use this package. Yeah, that's exactly essentially what I did is I used there's a package called homotopy continuation in Julia, in language Julia. That's quite nice. And that is what I used to do all the path tracking. So all I did was kind of put in a study system, and then I used the default path tracking. So yeah, I didn't really have to mess with the new way of stuff.
Just a follow-up question. During the algebraic geometry, the slides which you are showing, during the mapping, you showed that it's a convex mapping, right?
That's one option to do, yeah.
Okay, so what other kind of mappings do you follow?
Yeah, so in this case, we got in this case the mapping was convex, and you have to justify that a bit. In other cases, you could do like the homotopy parameter t, that's the one you vary from 0 to 1. You could just put powers of t on each monomial, and when t equals 0, you have to kind of deal with some of the solutions diverging, but when t equals 1, that would be totally good. So this is kind of more of a polyhedral system. And then there's a bunch of other things that people do, other different types of homotopies that people consider ridiculous.
Sorry, I have another question.
Yeah.
So the moments, the solutions to the equations which we found, what kind of space we are looking for when we are obtaining these kind of moments?
So what we want is we want them to be statistically meaningful. So we want to live in the space of simplex cross positive real orthant cross real space for the power. But we solve everything over the complex numbers because they're algebraically closed, and so then we can actually use these homotopy methods.
Thank you so much. I have a question from the chat. It's from Rohit. Are there any specific problems you have applied this to? That is, example, in any physics problems, or have you focused on pure on the abstract mathematical model thus far?
Yeah, so I think I did a toy example with some real data, but it was like not. Long story short is no, we haven't. Yes, we would love to, like, I mean, I think that'd be a really nice next step to do is to consider an actual data set, right? Oh, I've done like sample data, right? But like sample from Gaussian however many times, whatever. But not really any kind of full real data set. But I think that would be like, of course, once you work with real data, everything goes down. So, yeah.
Do you think this kind of technique can be applied to resource constrained machine learning, where with one fence you're taking into account meaningful data rather than taking the data for training?
Oh, I'm not sure. I haven't thought about that. I don't know enough about that problem, but maybe after you tell me, I can give you a better.
Right, because what you're looking for is, from a statistical standpoint, statistically important search that we are looking at. And when you are provided with the enormous amount of data, but your computer or a device is not sufficient to take all of them, then you decide upon what you want to take a meaningful one.
Yeah.
So first, very interesting. I was not so much distracted by my computer. I was consulting and comparing. Very interesting. Two questions. Actually, I have many questions. Let's start with two. The number of Gaussians, is that the determined, or do you know of an optimal way of identifying the Gaussians? So let's go with that one. And
yeah. So this is in general a challenging problem in and of itself, right? Even for like k-mean clusters, right? You know, it's like that's a much simpler version of this somehow, right? And so there exist heuristics, right? You know, I think with K-means, they always show these elbow plots, right? Where at some point, once you hit a certain K, the error seems to really not drop off that much. I know there's some work of Elizabeth Gross, who's used tools from numerical algebraic geometry to predict the kind of heuristic that we use when we did like sample data is, okay, I start with one Gaussian. I look at it and maybe we can even start with, maybe we start with two. Maybe we said, okay, we're not in the Gaussian. So we start with two Gaussians, we run through our algorithm, and we kind of see what we get, right? So one is you might not get statistically meaningful solution when you solve the polynomial system. So that tells you, you know, that either you don't have enough data or that you have the wrong model selection, right? And so then what we do is consider, okay, three Gaussians, right? And see how that fits. So you just kind of build yourself up until you're like, well, you know, this kind of looks reasonable. So there's heuristics, not maybe the best ones, but yes, that's some like a very interesting and kind of deep problem in its own way.
And that's connected to the second question, which relates to addition.
Yeah.
The thing is, if we have a number of Gaussians, then can we infer that the underlying process that we're studying is actually comprised by multiple Gaussians superimposed, and that number matches the number of Gaussians? That's one question. And the second is, in practice, we move this to do a statistical inference. So how to conduct a statistical inference in these objects? Do we go by each one of the individual distributions, or do we go with the cell?
Okay, so what was the first question?
So the first one is, if we observe that a number of Gaussians give a good representation of the data, how much of an intellectual leap it is to assume that you have the same number of underlying processes driving the
Oh, yeah, that's a good question. I mean, I don't know. I think it depends a lot on your actual application, right? Because maybe, I mean, yeah, I think it depends a lot on the underlying application, right? Because you can have, you know, you could have maybe two subgroups in one Gaussian, right? Because they, you know, either have just similar enough distributions that one fits it. I mean, there's lots of instances where your data isn't Gaussian, but one Gaussian fits it quite well, right? And so like this kind of thing could happen. And so I don't know. I think that would be really application dependent. And then your second question
is about statistical inference. How do we go about statistical inference? Because something that is very important in the is to compare two cases, an intervention, a control, and so on. So we want to many times answer the question, are these two distributions same? So what is your take? Do we go with the ensemble or with the individual distributions that are being used?
I think you should go with the individual component as seen by this, right? Because if you went with the whole thing, I mean, these things are pretty similar, right? And so I think for these mixture models, you need to look at the individual components, right? At least in this case. I mean, maybe there's other mixtures of other densities that you don't, but at least in this case. And this example somehow isn't even the most dramatic. Like there's kind of lots of cases that where you get this kind of thing.
Yes, this is called hidden value. They know that hidden value. That's probably the process. Not a expression, but that's the one that you patent. You saw a data, but there was a very high. And from what you saw, you're not aware. And we figure out all the things there that they think they will usually range.
But like extrapolating harmonic analysis, take a signal that you
In a way,
a signal with a basis. You can use any basis. We, for convenience, use sines, cosines, and that ends up being the transport, etc. But it's just a matter of convenience. We can do it with any function, but we have to be on orthogonal basis. So wouldn't this be analogous in the sense that I can take Gauss Gaussian, like cosine analogy, harmonic analysis, or any other distribution, and build a mixture of any distribution, as long as I have the parameters of that distribution. Wouldn't that be accurate?
Yeah, so yeah, you can definitely, yes, you can definitely consider mixture models of other distributions, yes. But I mean, I'm not sure what kind of properties they would, like, I'm not sure if they would even have the universal approximative property, and, I mean, I guess this is like, somehow the assumption you're making when you put this framework on the problem, right? But like, I'm assuming that I've got a bunch of underlying Gaussian components. I mean, if this is the kind, if you trying to look at the if you're trying to get at the hidden variables, you like assuming that they're all Gaussian, but yeah, maybe they're not, and then this is a bad choice, right? Somehow.
Well, in the end, this ends up being almost a cultural object because we study Gaussian, we know the properties,
Yeah.
but somebody else could make a different choice. The
Yeah.
same way that we talk about the frequencies that
Yeah.
build the signal, we talk about the zeros
Right.
built in the orthogonal polynomials that can build the signal. It's just a convention that we adopt.
Yeah. Right. I mean, right. Yeah. Of course. And I mean, the reason we study Gaussians, though, right, is because they matter. Yeah. Exactly. And so, and also, quite a bit of data is naturally Gaussian. It's not like the most absurd assumptions to put on things, right?
That's very important because in practice, if the tallest person in the world walks in this room, the average height would change by what, half an inch. But if Bill Gates enters this room, the average income might change by a lot. So what is the applicability of these for flat tail distributions?
Yes. Okay. This is actually a question I've gotten. So one thing that's nice about Gaussian mixture models is that they can model fat tail distributions, right? But then it's like a little bit of a yes, and you can actually there's been a little bit of work on this, but like maybe 20, 30 years ago. But you don't assume that each component is Gaussian. You assume each component is a mixture of Gaussian, right? So then if you can iterate this process, right? But I haven't looked at what that would look like. Yeah. Yeah.
I have a couple of smallish questions and one small one. So if for the homotopic paths, I assume that Newton's method is not like required. You can use any numerical optimization, or is Newton's method really the only viable?
So yeah, so I got a question a lot under the rug, and so this is one of the things, right? Newton's method doesn't need to converge. We all know this, but the point is that if I take a step, if I know that in a neighborhood it will, and so then these predictive corrective methods just don't move outside that neighborhood, but I mean, ideally, right? And but there's a lot, but people have studied this a lot. And so maybe if your path is really curvy, you're not taking as many, you're gonna need to take many more steps to trace it. And there's, yes, many ways you can do this, right? And there's like adaptive step sizes you can take so that you kind of don't overshoot. Or if you do overshoot, and it diverges, that's actually not the worst thing that can happen because then you need to take a smaller step. But you could overshoot and converge to a different path, right? Like, I mean, there's lots of things that can go wrong. I don't want to, but it's quite, there's quite a bit of theory and people have studied it quite a bit. And like I said, in general, it's pretty reliable, but of course, yeah, not hard to construct examples where everything goes terribly.
And then, so for the cases where the mixed volume is very difficult to compute, does the total degree option become viable again, or is it still the divergence in the number of paths still make it not effective?
Yeah, so it depends how big it is, but that's where the total degree option is. I mean, okay, you saw in this case both bounds were exponential, right? So there's a limit, but the total degree bound was much more exponential, right? And so like in general, that's the issue, right? That's why we don't use these that's why we just like can't use these total degree methods. I mean, this little toy system I gave you at the beginning, I said this was a Kuromoto system, whatever that means. And like, there's examples there where the mixed volume bound is quite small, maybe on the order of 300,000, but the Bezier bound is 275 billion, or something like this, right? And so it's like, well, yeah, we can do 300,000, but we can't do 275 billion. So it's, So yeah, a lot of times that becomes the issue, is that if the polyhedral method fails, then at that point, the Bizu bound is kind of likely going to be quite a bit too big to do, at least on your laptop. But of course, there's a lot of different situations.
So yeah, so if the polyhedral bound fails, then the Bizu bound is probably even way worse, so it's not worth it.
Yeah, so if the polyhedral homotopy fails and the BKK bound is much less than the Bizu bound, in my experience, typically the point at which the polyhedral will fail is well beyond the point where doing a total degree is kind of close to realistic. But I don't know, maybe if you have a ton of computing power and you can parallelize things, then I mean, but there's other methods too. There's something called monitoring, which can maybe help you in this case, but I didn't talk.
So it also so in the two-dimensional case, you said you can only go up to K equals 4 or something, but that seems a little bit restrictive. So is that like a hard limit, or is that
no? So
what is the K equals 4?
So sorry, I didn't mean to say you can't go beyond K equals 4. I just meant to say you need to go up to at least K equals 4 by like just kind of counting. But then the issue is that once I'm at K equals 4, I've got 15 equations, but 12 unknowns. And so I don't need all 15 equations. And so it's kind of unclear which 3 I should drop. Intuitively, I should drop my highest degree ones because they usually higher degree polynomials and just more solutions. So for the sake of kind of computational efficiency, but still there's 5 of those. There's 5 or there's 4 equations. So then you've got, 5, choose 3 different polynomial systems to look at. And then this kind of persists, for all K and N, right, higher than this. It's like, how do you even pick which moment system to look at? And I should have mentioned as well that once we get to 3-dimensional space, this algebraic identifiability or this kind of complete intersection behavior starts to fail. So then maybe you think you have enough moment equations, but you need to go up even higher because your variety is too high dimensional. You don't get cut down to finitely many solutions. So things just kind of get much more complicated. It's much more complicated to even write down the problem you want to study.
Okay, this actually leads into my final, last small question. So in the case where you have your mixture, your single mixture actually really is like maybe 2 mixtures that are very far apart. So like, say you have like one mixture way over here and another mixture with the mean way far away. So like effectively you can divide your problem into 2 subproblems and reduce the overall complexity of the big problem by like that. Is there a way to reliably identify that situation, or is it like safe to do that? Like do a K-means first and then say, okay, really we don't have one 9-dimensional problem, we have 3 K equals 3 problems.
Yeah, we haven't really studied this setup, but yeah, I mean, that makes a lot of sense, right? If you Gaussians are well enough separated that you can like literally see, I mean, like I can see 2 Gaussians, right? Then somehow, if that's the data you're seeing, of course you should treat, that, yeah, but we didn't consider any kind of like systematic framework that if I just input data, this is good. Yeah, there's probably other ways.
Any other questions?
Sure, yeah.
There's actually kind of benchmark that there was 8-9 years ago there was a paper for the decomposition. I think it has quite that was the same problem, but that was
Yeah.
And recently there has been a lot of work more difficult. This moment, this way of looking at the problem kind of fits the evidence.
Yeah.
Since they proposed techniques for the exact, same framework,
Yeah.
it kind of makes sense to okay compare, and this. I think the old paper maybe it's implemented, but theoretical people don't implement their stuff.
Great.
It's at the benchmark.
Yes, that's a massive issue with like there exist theoretical CS papers in this, and our results aren't quite in the CS framework. Right? We don't say, oh, if you have n samples and with probability 1 minus delta, you whatever. Like that's not the flavor of the kind of results used. So we compute stuff to say, you know, look, it's kind of, but then with the theoretical CS stuff, they can't, it's like, it just doesn't, it almost doesn't even make, yeah, yeah, it's, so, yeah, we tried to, and we can't benchmark, but there's other papers, like, I know Gio and me has a paper, and Joe, trying to look at this problem through tensor decomposition instead of, it's like a similar framework, but you set it up as a tensor decomposition problem, and then they use, yeah, convex optimization to try to solve the non-convex problem, and, I don't remember.
Those are baby bench.
Yeah, I think so. I don't think we. I think those. Yeah, I don't think we did though. I mean, yeah.
All right. Thank you very much.
Thank you.
Great talk.
Thank you.
Thank you.